Hello guys, this is Dave. Today we are going to study part 2 of gravitation, okay? So earlier I had taught you the gravitation due to a ring, okay? This was the ring and we calculated the gravitational force, okay? These were the components if you remember in my last video, and I just, resolved them along this line because resolving along this axis would cancel out the vertical components, alright? So let us now first calculate the potential, okay? I had earlier calculated the potential due to the ring. Now I want to calculate the potential due to thin spherical shell, alright? So how do we calculate it? For example, you see this is a sphere, okay? This is a spherical shell. Shell means inside this is hollow. Only this is a shell, inside this is hollow, and this is a sphere, okay? This has a radius r. Okay, so I want to find out the gravitational potential of this spherical shell, say at a distance z. Okay, consider the distance z. Alright, sorry. Let us consider this r. Okay, so what do we do now? You see, we can divide this spherical shell into concentric discs, or we can say concentric rings, not disc, because disc for this to happen it should be a sphere which is not hollow. So we divide into concentric rings. For example, this is one ring, okay? This is just one example of a ring, and this is the width of the ring, okay? So now, since this is a shell, mass would be dependent on area. As I already told you, if this is hollow, mass is dependent on area. So let us consider this mass of spherical shell to be dm. Okay, so what would be dm? Dm would be mass of the spherical shell divided by the area of spherical shell, which is 4 pi r squared, times dA, which is the area of this ring. Okay, so this is the distance r. Let me give you this very clearly. Okay, you see, this is r. Okay, this is also r, since it is touching the surface. Let us consider this angle to be theta. So what is this angle? This angle is a very small angle. Okay, very small angle, so we consider this as d theta. Okay, differential angle which is very small. So you see, now as I already told you in an arc, this distance ds, this is r, and this is d theta. So ds is equal to r d theta, right? Similarly, in this ring, you can see the width of the ring to be ds. So ds would be r times d theta. So we have the width of the ring as ds equal to r times d theta. Alright, this is the width of the ring. Now what? Now we calculate the circumference of the ring. Circumference times width will give the area. Okay, what is the circumference? First we need to have radius for the circumference, because circumference is 2 pi r. Okay, so if we consider this as, because I have written this as r, we consider this as r naught. Okay, so we consider this as r naught. So what would be r naught? This is a right triangle. Okay, so you see, this is r, this is theta, and this is r naught. So sine theta would be equal to perpendicular by hypotenuse, so r naught by r. So what would be r naught? R naught would be equal to r sine theta. Okay, alright, so we have the radius of the ring. Okay, so what would be the differential area of the ring? Because I have to calculate dA over here. Differential area of the ring would be the width of the ring times the circumference of the ring. Okay, this would be the differential area. So dA would be here equal to 2 pi r sine theta times r d theta. So this would be r square sine theta d theta. Alright, so this is the differential area of the ring as I have it. Okay, so what would be the mass of the ring over here? This would be m divided by 4 pi r squared times 2 pi r square sine theta d theta. Alright, this cancels out, pi cancels out, and this cancels out. So we have left with us as dm equal to m by 2 sine theta d theta. Alright, we have dm as this. So now I want to find out the gravitational potential. You see, in the earlier part, I always assumed in the ring gravitational potential to be G dm by R. This was R, okay, in the earlier part, in the last video. Alright. Whatever this may be, the distance, for example, this is the differential mass G dm by R, okay. So this was the gravitational potential and this would be minus, right? So in case of this spherical shell, this is the spherical shell. This is the distance R and this is the ring, spherical ring, okay. So what would be the gravitational potential due to this one ring? What would be the gravitational potential due to this one ring? You see, let us consider this as Z. Alright, we consider this as R, okay, and this was theta as I already told you. Alright, so we have this is Z, this is R, alright, and this is small r, because the distance of small r is from the center of the spherical shell, not the ring, okay. Distance small r is from the center of the spherical shell, which is O. This is R and this is Z and this is theta. So applying cosine rule. Now this is, I'm not teaching maths over here. You should know what is cosine rule. You see, cos theta is, you see, cosine rule, cos theta is, we square and add the two sides which contain theta, okay, and subtract it and subtract the square of the third side from it. You see, r square plus r square, we have summed the squares of the sides which contain theta and we subtract the square of the third side, okay, by 2rr. This is the general general use of this, and you don't need to derive this, okay. So this is cos theta, right? This is r square plus r square minus z square by 2rr. Alright. So cos theta was r square plus r square minus z square by 2rr. Okay. What would be the differential of this? You see, differential of this would be minus sine theta d theta. Okay, you should know differentiation. I am not going to teach here. R and R would be constant because small r would also be constant. Capital R to constant hai hi. Small r will be constant because we have to find out the potential at this point. This point is going nowhere. P is going nowhere, okay. This R should also be constant. Only this Z will not be constant because of the variation of mass. You see, for example, this is a spherical shell. We take the ring over here. This would be Z, and now we take the ring over here. This would be Z. So Z has increased, okay. But the R is constant since R is taken from the center, alright. So minus sine theta d theta, this to become 0, this would be minus 2z dz by 2rr, alright. 2 cancels out, minus minus cancels out, sine theta d theta becomes z dz by rr. Okay, so what would be the mass now? dm would be equal to m by 2 times z dz by rr. Alright. Yeah. So m by 2 z dz by rr. This would be the differential mass. Alright. What would be the potential now? You see, the differential potential would be dv equal to minus g times dm by z. As I already told you, for a ring, this would be the differential mass, and now I am taking the distance from this differential mass, which was z, okay. So minus g dm by z, and we just substitute the values over here, g m by 2 r z dz by z. This cancels out, okay. So dv is what? dv is minus gm by 2 r times dz. Now we integrate this, alright. Since this is a differential, we have to integrate this. Now tell me one thing, this will be integrated from 0 to v, alright. What about z? You see, z would be integrated from, first of all, let me explain you this way. dv was minus gm by 2 rr times dz. Now you see the limit of dz. If I take the mass over here, this is what? You see, this distance is r and this distance is r. Okay, so this distance would be small r minus capital R. Alright, small r minus capital R. This would be the distance. So if mass is taken here, this is the extreme point. Alright, so if mass is taken here, the potential distance would be r minus r. If I take another extreme, what would be this? Since this is a center, this is r, and from center to this point P, the distance is small r, so it would be r plus r. Alright, so z can vary from r minus r to r plus r. Alright, this is the maximum limits of z. Alright, so let's see, minus gm by 2rr, and this would be r plus r minus r plus r. R gets cancelled. So this would be minus gm by 2r times 2r. 2r gets cancelled out. So v is minus gm by r. Alright, gm by small r, right? V is minus gm by small r. This is the answer. Okay, so you see, this is in consonance with the Gauss theory, because you know, Gauss theory assumes in electromagnetic field, for example, which can be similarly applied to gravitational field also. If this is the mass and we have to calculate any potential or field over here, we assume this mass as 1. I mean, if the mass is m, we assume this as point mass. Okay, since why it is being assumed as point mass? Because the whole point would be concentrated on the center. Alright, since whole mass would be concentrated on the center due to the theory of center of mass, the effective distance would be only r. So if we try to calculate potential, we can easily assume this point as center. We can easily reduce this figure to like this, you know, this is a point and this is a point. Calculating point between two potentials, calculating potential between 2 points. This is P and this is O. Virtually this has a mass m. Okay, so there is no need of taking the sphere. This has a mass m, this is r, so V would be equal to minus gm by r, which is right. Okay, and obviously E would be equal to gm by r square, and that would also be minus, because the field of the gravitation would be directed inwards, because it is an attractive force. Alright, so we had V equal to minus gm by r. What would be field? Field is described as minus dv by dr. Alright, so this would be equal to minus gm by r square. This would be the answer. This is equal to minus gm by r square, and we can put this as r cap. This would be the gravitational field. Okay, since minus, we can first we differentiate this 1 by r. This would be minus 1 by r square, and minus would cancel out, and again the minus, so minus 1 by r square gm. This would be the gravitational field. Okay, I am taking E, but you can also assume as G, because I am not assuming this because I have taken already taken this as gravitation constant, so I am assuming this as E. Alright, don't mistake it for electric field. Alright, because mass m is involved here. Alright, so we saw that this was a spherical shell, and we had to calculate the gravitational potential at a point P which was outside the shell. Okay, so we had arrived at answers V and E. I'll explain you how E is minus del V by del R. I'll explain you. Alright, you don't need to worry about this. I'll explain you the whole derivation. I will, and I'll clear your concepts according to this. And now I want to know what, first let us concentrate on potential this time. Now I want to know what would be the potential if I take the point inside the sphere. For example, this is a cross and this is a point P. So I want to know what is the potential at this point. This is a spherical shell, and this point P is at a distance small r from the point O, which is the center. So you see, we just assume the same equation, because ultimately the same equation would arrive if we calculate it. Minus G, what would minus gm by 2 rr dz. Okay, this was the equation, and you see this was dz. Earlier this was dz. You see, earlier this was dz, but now this is z. Sorry, yeah. Okay, So what are the far reaching maximum limits of z that z can go? First limit would be here at extreme point. What would be this? This would be capital R minus small r, right? So this would be capital R minus small r. And what would be the next limit? Next would be capital R plus small r. Alright, capital R plus small r. Right. Since this is the maximum limit, this is capital R plus small r, and this is the minimum limit. This is capital R minus small r. Now we can easily find out the potential. V would be equal to minus Gm by 2 RR, and this would be capital R plus small r minus capital R plus small r again, okay? So this would cancel out, and V would be equal to minus Gm by 2 RR times 2 small r. Small r gets cancelled now, you see. So V would be equal to minus Gm by R. So what can we say about this potential? Well, we can say about this potential that potential is constant inside the spherical shell. Alright, just remember potential is because V is actually independent of small r. Alright. So potential is actually constant inside the spherical shell. For a point P, small r was constant, yes, but for any other point it can vary. Alright, in the earlier question I had assumed small r is constant because I had to calculate potential at this point only. For a particular point, yes, small r can be constant, but for any other point, small r can vary. But here V will not at all vary. Alright, here we could have varied the potential by varying r. But how can I vary the radius? It is always constant. Alright, so V is constant inside the spherical shell. You must note this point, this is a very important point. V is constant. Potential is constant inside spherical shell. Gravitational. Gravitational V is constant inside spherical shell. The very important point. Alright. So V is minus Gm by R. What would you expect the gravitational field to be? I had already told you field is minus del V by del R. I'll explain you what is this. This is partial differential, but since we have only one constant, this becomes simple differential. So this is 0 because R is a constant over here. Alright, this is 0 because R is a constant over here. So field inside spherical shell is 0. Field inside spherical shell is 0. Just remember this. This is a very, very important statement. They can ask you, you just have to write, you just have to know the answer because they will give you 4 choices. Alright, they'll write Gm by R, Gm by 2R, 0 and Gm by 5R. So, don't waste your time calculating the mathematics. Just see whether it is spherical shell or not. If they have written spherical shell and they have asked that what is the field inside spherical shell, just mark it as 0 because this is 0 actually because potential is constant over here. Okay, so don't waste your time calculating the mathematics and calculating the potential, then arriving at field. Just mark it as 0. Okay. Alright, so we had V equal to minus Gm by small r. This was when R was greater than capital R. Capital R is radius. And we had V equal to minus Gm by capital R. This was the case when R was smaller than the radius. Okay. Alright. This was the case when R was smaller than the radius. Now, this can also be equal to because the point mass was taken from the spherical shell only. So, this can be equal to also. Okay. So, let us first, plot this. I have to plot potential and R, small r. How do we plot this? You see, this axis is R, this is V. You see the direction in which this is given, this means positive and this is also positive. Hence, this would be the negative direction. Okay. So, since V is minus Gm by R, okay, so what is this? This is when R equal to 0, or we can say at the center point. Okay. So, at the center, since the potential inside the sphere was constant, so at the center this would be minus Gm by capital R. Okay. So, we went on, the potential remains constant. and now we reach a point R. Okay, so at R, Gm by R, at R what happens is both the potential become same, because when R equal to R, this will be Gm by capital R and this was also Gm by capital R. Alright, so now after R, what happens is this changes, because V is proportional to 1 by R now when R is greater than capital R. So you see this graph almost represents xy equal to constant. Okay, this is a hyperbolic graph. Alright, so when you plot a hyperbolic graph, you can see when x and y are positive, what happens is when x tends to infinite, since y is equal to c by x, so when x will tend to infinite, y will tend to 0. This means like this. And when y will tend to infinite, x will tend to 0. So this means like this. This will be the graph of the hyperbola. Okay. Since this is a hyperbola, when we invert it, because here y is positive but here v is negative, so we have to invert this. R is constant. So we get a graph like this. Alright, this is the graph. So when R reaches infinite, V reaches 0. Alright. Obviously, this is also true because I referred as the reference point of potential is 0 when R is infinite. Okay. This is the graph. You can see the graph over here. This is the graph of V versus R. Just remember this graph. They can ask you questions from this graph. They can, in the 4 options, they can draw different types of graph, like this. One can be like this, one can be like this, and one will be like this. You have to mark this as correct. Okay, just remember this. This is for remembering purpose. Okay. Alright, so let's move on to the next question. I have to calculate potential for a solid sphere. Okay, earlier I had calculated for a hollow sphere. Alright, so this is a solid sphere of mass m. This means that inside the sphere there is mass. Okay, it is not hollow. I have to calculate the potential at the point P from the center of the sphere at a distance R. So how do I do it? First, since the radius is constant, mass is constant, and the sphere is continuous, okay, then the density will be constant. So density is rho, this which is mass by volume. What is volume? 4 by 3 pi r cube. Okay, so this is the volume. Now what I do is I divide the sphere into concentric spherical shells. Okay, the sphere can be thought to be made up of several concentric spherical shells like these. One such shell I am taking, it has a radius x and a width dx. Okay, so I want to find out the volume of the spherical shell. Since this is an infinitesimal spherical shell, the volume would be dv. Okay, this would be the surface area of the spherical shell, 4 pi x square times the width, which is dx. So what is the mass? dm. This would be rho times dv, because the sphere is continuous, so density will be same everywhere. This would be 3m by 4 pi r cube times 4 pi x square dx. Alright, 4 pi gets cancelled out, so we are left with 3m by r cube x square dx. Alright, this is what? This is dm. Now, what is the element potential due to this spherical shell? If you recall earlier, in the earlier questions, I had calculated the potential for a spherical shell when the point lie outside the spherical shell. Alright, this was m. Suppose this is a spherical shell, the potential came out to be minus gm by r, right? Same equation we can apply over here. The difference is only that I am calculating the differential potential shell. Okay, and this mass becomes dm, so this would be minus g by r dm. Okay, you see, since r is independent of the expression of dm, since dm is not a function of r, here is x, so I can directly integrate this by excluding r. So we have v equal to minus g by r integration of dm. So x will go from 0 to r. Alright, 0 to capital R, because after capital R there is no sphere. Okay, it is space only. So this would be r cube by 3, this would be cancelled out, and we are left with m. So we have the answer minus gm by r. Can you see this answer is exactly the same as that of spherical shell? So, when a question comes, when you are given a spherical shell or a sphere, and when this option is given, only this is correct if the point lies outside the sphere, okay, or the spherical shell. Alright, so now I want to find out the potential inside the sphere. What would be the potential inside the sphere? Let us take a point P inside the sphere at a distance r from the center of the sphere, okay. This sphere is solid as all we know, and this sphere is continuous, so the density of the sphere would be continuous. This would be 3m by 4 pi r cube, okay. I have told you this, okay. Now, since the point P is here, I am taking a view of this shell. You see, this is a spherical shell, okay, and this is a point P. This is point O, this is R. So you see, there are two spheres over here. One, we are placing the sphere which is passing through point P, alright, and one is the outer spherical shell which has a radius x and a width of dx, alright. So we have two spheres over here. Now if I want to calculate the potential at P, I have to calculate the potential due to inner sphere which passes through P plus V of outer sphere, okay, which has a radius x and width dx. So how do we do this now? You see, first of all, I have to calculate the differential mass of this inner sphere. This inner sphere would amount to m by 4 by 3 pi r cube times 4 by 3 pi r cube. Okay, since this sphere has a radius r and the volume would be 4 by 3 pi r cube, okay. So 4 by 3 would be cancelled over here. So we have m r cube by r cube. This would be the differential mass due to this. Now, due to this sphere, let us assume this small sphere to be A and this outer spherical shell to be A dash. So we have V equal to V of A plus V of A dash. Alright. So what would be V of A dash? You see, dV of A would be, dV of A would be equal to minus G dm by small r. Okay. Since this point P is lying at the edge of the sphere A and the distance from center is r, so we know that this is minus G dm by r. So it is simple, and now we can calculate this. Minus G, what was dm? M by r cube. This r would be cancelled out by r cube, so this would be minus gm r square by r cube, okay. And we have integrated this. I am integrating this, okay. So this is the potential, okay, V of A. Now I want to find out the V of A dash now. You see, this was small sphere which is A, and this point P, and this is small r, and this was spherical shell. Now potential due to this spherical shell of radius x inside, as I already told you, potential due to spherical shell inside is constant, right? And since it is constant, it is minus G dm by capital R. Okay, so what is this radius over here? This is x, so this will be minus G dm by x, okay. This would be minus G dm by x, and this would be equal to V of A dash, okay. This spherical shell is varying, okay, from R to capital R, okay. This is the original sphere. This shell is varying from small r to capital R, okay. So now what would be the differential mass? This would be m by 4 by 3 pi r cube times 4 pi x square dx, okay. You see, this small is a sphere and this is a spherical shell. There are differences, alright. We have not assumed inside one as shell, okay. I have assumed inside one as a sphere and outer one is a spherical shell. Since this being a shell, this introduces a width dx, so this is the mass dm of this shell, okay, which is A dash. Now what would be the potential due to A dash? This would be equal to minus G dm by x. Since point P is lying inside, so this would be minus G dm by x. This would be minus 3 gm, 4 pi has got cancelled by r cube, x will cancel this, so we have x dx. Now this will vary from small r to capital R. V of A dash would be equal to minus 3 gm by 2 r cube r square minus r square, right? So what would be the potential, net potential? This would be equal to minus G m r square by capital R cube by capital R cube minus 3 gm by 2 r cube times r square minus r square. This would amount to minus 1 by r cube, this will be constant, gm by r cube will come out, r square minus r square plus 3r square. So this would be, and 2r square, na? So 2 would be coming out, and 3r square, okay, so this would be 3 capital R square minus small r square. This is the answer. Alright, yeah, this is the answer of the final potential which is inside the sphere. Okay, minus gm by 2 r cube times 3 capital R square minus small r square. Now what would be the potential at the center point of the sphere? You see, this potential is not constant. Okay, this is differing with the spherical shell where potential was constant. Here potential is not constant as r is varying small r. So when small r is 0, so V at O, okay, V at O would be equal to minus gm by r 3 by 2. Alright, this is the answer. So what answers do we have? Okay, V for spherical shell, okay, outside this would be equal to minus gm by r. R is greater than r. Inside this would be equal to minus gm by capital R. R is smaller than r. Okay, V for sphere, outside this would be equal to minus gm by r. R is greater than capital R. Inside would be equal to minus gm by 2r cube 3r square minus r square. R is less than capital R. Okay, these are the expressions. This is very important, and you can just remember these expressions. It will be very helpful for MCQs. You can solve it in a very short amount of time. And V at center for sphere solid, this would be when r is 0, so we have minus 3 gm by 2r. Alright, this is the answer. These are the answers I have derived. You can check them. These would be correct. Okay, alright, so now I want to plot V versus R for a sphere. You see, V at center, this was minus 3 gm by 2r. V when r was less than r, this was equal to minus gm by 2r cube 3r square minus r square. Okay, and V when r was greater than r, this was minus gm by r. So you see, first we draw these two axes. This is r and this is V. Arrows indicate the positive direction and this arrow will indicate the negative. Okay, so since V is negative, we start from here. For example, this is the value of V when r equal to 0. Since this axis is 0, so this is the value of V, minus 3 gm by 2r. Okay, and here we take r equal to r. Alright, so when r is less than r, we apply this expression. Okay, now let's open this expression. This expression amounts to V as a function of r would be equal to gm by 2r cube r square minus 3 by 2 gm by r. Okay, so this expression amounts to this. As we can see, if we differentiate V with respect to r, since this is a constant term, okay, if we differentiate V with respect to r, we have dV by dr equal to 2 gm by 2r cube r. Alright, 2 gets cancelled out. So we have gm by r cube times r. Okay, so this is positive. This means the slope is positive. V versus r slope is positive. Hence the slope must be in an upward direction. It cannot be a downward direction slope. Alright. since the slope must be an upward direction slope, this means, and since v is proportional to r square, so y is proportional to x square, this means it is a parabola. So we can see the slope like this. This could be the slope, okay. So when r becomes r, what happens is when r equal to r square gets cancelled out, so we are left with gm by 2r minus 3 by 2 gm by r. So this means minus gm by r we are left with. So this value is obviously greater than minus 3 by 2 gm by r. Hence the curve is correct. Alright. Alright. So when r equal to r, this value is minus gm by r, and hence the value should be increasing. This curve is correct. Okay. So after r is greater than r, we see that the curve changes and v becomes proportional to 1 by r. This is actually a hyperbola when x equal to c by y, or we can say y equal to x upon c, c by x. This means I am taking y equal to c by x. This means when x reaches infinity, y would reach 0. When y reaches infinity, x would reach 0. This kind of curve will be obtained. Okay. Yeah. So this means when r reaches infinite, then v should reach 0. This means the curve should be like this. Okay. This is the curve. Alright. This is the curve of v versus r for sphere. Okay. This is the curve. You can see this part. When r gets greater than r, this is the same for spherical shell. Okay. This part, the second part, is same as that for spherical shell, but in the first part this was constant. Now it is not. Okay, this is the difference. This is the primary difference you have to see. Okay, on to gravitational field. I am going to teach you something about gravitational field. You see, in electric field, what happens is there is a charge q, alright, and field is assumed around its space. Okay, this is E, which is electric field, small e for electric. Okay, so how do we know that there is a field around it? You see, if you bring a test charge q naught, it will experience a force, a repelling force F. Okay, and that force will be dependent on the distance between them, and that force was k q1 q2 by r square. This was according to the Coulomb's law. Coulomb's law of attraction and repulsion. So what happens is F would be equal to here k q naught q by r square. So if this test charge is not there, then it doesn't mean that space is empty. Space is filled with the electric field produced by the charge. So we can bring the charge q naught over here and we get F by q naught equal to kq by r square. Okay, this F by q naught, when charge is not there, this is the electric field produced by the charge q at a distance r. So if there is a charge q and we have to calculate the field at point p at a distance r, so E at p would be equal to kq by r square. Alright, till this I think you have understood. The same applies with gravitational field. If there is a mass m and we bring a test mass m naught, it will feel an attractive force because gravitation is always attractive. So force of gravitation would be equal to gm m naught by r square if the distance between two masses is r. Alright, so if I replace the test mass, we have F by m naught would be equal to Eg. This is the gravitational field, which will be equal to gm by r square. Okay, so this is the gravitational field. This means that the space is not empty, it is being filled with the gravitational field if in case of mass. Alright, so the field due to gravity is gm by r square for a mass m at a distance r. Alright, so you see, if there is a mass m and there is a test mass m naught, it is obvious that the test mass will experience an attractive force. We can also write this as F equal to G M M naught by R square. This was E, so we can write this as M naught times E. So F becomes M naught times E, alright, where E is the gravitational field. Okay, from now onwards I am using E. This is gravitational field. Okay, I am writing this down specifically. Okay, so you see, in if this test mass is experiencing a force, obviously it will do some work since it will get displaced. So the work done would be equal to dw equal to F dot dr. Alright, if this is the r and it travels or displaces a small distance dr. Alright, here the work done would be positive as the displacement of the test mass is the same as the direction of force. Okay, so this would be equal to me dot dr. Alright, so now I want to calculate the change in potential energy. If you're talking about potential energy is generated when work is done against the force. Okay, so I have taken the work done by the force. So if I displace the m naught in the opposite side, since F is here, m naught is here, if I displace it opposite side, then the potential will be generated du. Okay, and since it has not moved, only displaced, so the change in kinetic energy would be 0. So du would be equal to negative of dw. Alright, this would be equal to minus me dot dr. This would be the change in potential energy. Alright, since potential energy would be generated. Okay, so what will be the potential now? Potential energy has been generated. What would be the potential now? You see, potential dV is in the electrostatics is du by q. Alright, so this means the potential energy generated is q times the potential difference. So here similarly the potential will be equal to the potential energy by mass. So this would be equal to dV would be equal to minus E dot dr. This would be the potential generated. Okay, so in nutshell we can say, if we exclude the force, this means for a mass m at a point P, the electricity, the gravitational field is E. So if I just take a point further from it, then potential is generated. Okay, this potential is minus E dot dr. Okay, so now we integrate this, dV equal to minus integration E dot dr. So we integrated from, let's say, coordinate r r1 to r2. Okay, we can take first of all we have to take a reference point for this. Since potential we have not defined, first potential needs to be defined, so we have to take a reference point. For example, V at R0 should be 0. From that reference point we can define any potential at V at R. So if we take from R0 to R, this becomes from R0 to R. Okay, so V at R would be equal to minus integration R0 to R E dot dr. This would be the potential. Alright, now you see, V of R was minus integration R0 to R E dot dr. This was the potential. Now these are vectors, so let's cut them down to scalars. I mean, let's cut them down to individual components. So E would be equal to EXI plus EYJ plus EZK. Alright, and dr would be equal to dri plus drj. Sorry, this would be dxi plus dyj plus dzk. Alright, so what would be E dot dr? E dot dr would be, since I dot j would be 0, I dot k would be 0, I dot I would be 1, so this would be Ex dx. This will not be dot because vector is only I. Okay, ex and dx are not vectors. Plus ey dy plus ez dz. Okay, so the dot product yields ex dx plus ey dy plus ez dz. So what will be dv? dv was minus e dot dr. So dv would be equal to minus ex dx minus ey dy minus ez dz. Alright. So you see, if in one direction I have displaced a particle, say x, this means y and z are constant. We can easily see this. This means y and z are constant. So this means dy and dz would be 0 since y and z are constant. If I displace the particle along x direction, okay, this is the mass m, this is the test mass, and if I have displaced it along x direction, y and z are constant over here. And also since y and z are independent of x, this means dy and dz would be 0. So we have dv equal to minus ex dx. Alright, if it is displaced in the x direction. So you see this term, now we want to define the field ex, because ex is the only field which will displace the mass in the x direction. That's why I have taken y and z constant, because I want to define this field ex. This would be minus del v by del x. Okay, you see I am not taking dv by dx. Why? Because ex has only displaced the mass in the x direction. This means the displacement along y and z are not there. Y and z are constant. Since v being a function of x, y and z all, I just cannot differentiate it like d by dx. d by dx means that it is not partial differentiation. This means y and z are function of x. So it can be written in this way if we want to write dv. But if we want to write ex, we have to write it in negative del v by del x. Okay. So for example, if v equal to say minus kx square plus y cube plus z cube. Okay. Now I want to find ex. Ex would be equal to minus del v by del x. Okay, what would be minus del v by del x? It would be minus 2kx plus 0 plus 0. That's it. This is minus 2kx. Okay. Del by del x means we are only differentiating with respect to x. Okay. Not with respect to y and z. This indicates that x is independent of y and z, and this differential is independent of y and z. Whereas d by dx would indicate that this differential is not independent of y and z. Similarly, ey would be equal to minus del v by del y. In this expression, it would be equal to minus 3y square. Ez would be equal to minus 3z square. Okay. So we have ex equal to minus del v by del x, ey equal to minus del v by del y, and ez equal to minus del v by del z. Alright. This I wanted to explain is a very important concept. Okay. So guys, this was my analysis. Gravitation is a very big topic and it is a very important one. Okay. So I'll continue with gravitation for one more video. We'll solve problems also. We'll solve the problems of H.C. Verma. Okay. This is a very important book. You have to study H.C. Verma also. And you have to study H.C. Verma by heart. Okay. Solve each and every question of it. Each and every question. It is very helpful for NEET and IIT. Okay, NEET exam, I mean especially for NEET exam, if you solve H.C. Verma by heart, your NEET exam is almost done. Okay. And much of IIT is also done, but I mean the concepts you can understand by H.C. Verma very clearly. Okay. Please like, rate, review, subscribe. Thank you.